Today, we'll discuss the past year of Term 1 in 2022, Section 8. By the way, this is a copy that I found in Telegram group and it is not a clean version. And then the Section B is also missing. So if you read my message here and you have the soft copy, please do share it with me so that I can also do the video discussion and share to others as well. So let's begin. First question is about the scalar product of two vectors. So the answer is quite obvious. It is answer C, work. Okay, it is the example that we use when we talk about the scalar product in the first chapter. For answer D, area, it is the scalar product, not so-called scalar product, but it is a product of two scalar quantity. For example, for a rectangle, it is the product of the length and the width of the rectangle. So I hope this is clear for you. We move on to question number 2. A ball is released from rest at P and the ball moves along a smooth slope. So the smooth means there is no friction. Okay, and the horizontal surface as shown in the diagram. The ball rebounds elastically at Q and stops momentarily at P. So which velocity time graph represents the motion of the ball? So this is quite clear that is when it's moving along a smooth slope. So since it's a frictionless, so there's an energy conservation between the potential and the kinetic energy when it go up or when it moves down the slope. So when it is moving down, so the potential energy is converted to the kinetic energy. So you can expect that the ball is accelerating. So the velocity of the ball should be increasing. And then when it reach on the horizontal surface, the velocity will stay constant. Okay, we also assume that the surface here, okay, is also smooth. It is frictionless. So when it is a rough surface, okay, we can observe that the ball will decelerate like what happened in the actual practice. So when the ball hit the Q and rebound elastically means that the kinetic energy is conserved. And it is a wall here, and biologically the wall should be still stationary when it is hit by the ball. So the ball shall rebounds with the same velocity, but in the opposite directions. So that's why the velocity become a negative value. And when it go up the slope, it will undergo deceleration until 0 meter per second. So this should be the answer for this question, and the answer should be A. We move on to question number 3. An object of mass 2m moves with speed v and collide head-on with another object of mass m, which moves with speed half v in the opposite direction. If the collision is an inelastic collision, what is the speed of both objects after collision? So quite simple, it is an inelastic collision. So we can use this formula that m1u1 plus m2u2 equal to the total mass multiplied the final velocity. So let's put in all the values given. So the first mass, okay, it is a 2m, okay, 2m multiply v1, okay, multiply v, okay, plus m2, so the m2 is m, and the velocity is negative half v, okay, so this should be a very clear, should be a good reminder for you that the velocity is negative because it's moving to the left. And then we have the total mass m plus 2m multiply the final velocity. So simplify the equations. On the left, we have 2mv minus half mv, so it's 3/2 mv equals to 3m multiply the final velocity. So from here, we can see that the final velocity will be equal to half v. Okay, the final velocity is equal to half v when we cancel 3m. So the answer is B. Next, we look at question 4. Block of mass 4 kg slide down a plane which is inclined at 35 degrees. Then the force of 16 Newton is applied parallel to the inclined plane to push the block up and move at constant speed. So constant speed means that the force is in equilibrium. Okay, what is the coefficient of kinetic friction between the block and the surface of the inclined plane? So there's something fishy in this question, but first of all, let's go through the diagram here. So this should be the diagram that can be referred for this case. Okay, so we informed that the block is pushed up. So it means that we have a force 16 Newton is going up the inclined surface, and the factors that cause the block moving down is the mg sine theta, okay, the parallel component of the weight, and also the kinetic friction. So by looking at this diagram, okay, we know that it is at constant speed, forces are in equilibrium. So we have the 60 Newton force is equal to mg sin theta plus the kinetic friction mu r. So the reaction force will be equal to mg cos theta. Okay, you can see that in the perpendicular component, r is equal to mg cos theta. So this will be the equations representing this kind of condition. But when I try to do the calculations, we can get a negative value for the coefficient, which is not possible. Okay, you can try to do it on your own. We have the calculation as 16 Newton equal to the mg. So we have 4 kg multiply 9.81. Okay, multiply sine theta, sine 35, okay, minus the mu k, which is mu k, is what you need, is multiply cos 35 degree. Okay, so you can try to do the calculation on your own, and you will get negative 0.2, somewhere around there. So I guess there's some mistake in the question, okay, because we can try to check on the mg sin theta. Okay, there's the certain component that is in the test. Okay, so when we get mg sin theta, okay, 4 times 9.8, sine 35, okay, so the weight that is pulling the block down is 22.51 Newton, okay, which is in a direction that is parallel to the inclined plane. So if the force of 15 Newton is applied parallel to the inclined plane, it is actually less than the parallel component of the weight, which means that the block is not possible to move out. So that's the thing that I can notice from the questions. So I will leave the question here, and maybe you can say the answer is A, 0.2, but there's a bug in the question. So we shall move on to question 5. Okay, a block of mass 1 kg is placed on a smooth surface table, and the P is connected to a block of mass 3 kg Q by a cord passing a frictionless pulley as shown in the diagram below. So quite a popular diagram in the textbook. If Q is allowed to move downward, what is the velocity of the block as the block touches the floor? So a similar question has been discussed in one of my video. So we can actually obtain the equation in a very short time. First of all, at object P, we know it is T equal to ma. Okay, there's presenting the equation around object P. And for Q, we can see there's a tension, and there's also the weight of the Q. We have the weight Q minus the tension is equal to ma. And then we can combine these two expressions. Okay, we can get WQ, the weight of Q is equal to the total mass multiplied the acceleration. So from this equation, we can get the acceleration, and then we can apply the linear motion equation to obtain the velocity of the block. So let's try to do it. So the weight of the Q is equal to mg, that is equal to 3 kg multiplied 9.81, is equal to the total mass, 1 kg plus 3 kg, okay, that's the mass of the P and Q. So here we can get the A in a very short time. So what we have is that 3 times 9.1 divided by 4. So the extension is equal to 7.36 meter per second squared. So the next step is just apply the linear motion equations. So I think we can apply the v squared equal to u squared plus 2ax. Okay, we can see acceleration is 7.36. And then u is 0 since it is stationary at in the first minute. And then we have 2ax, the a is 7.36, and then the s is the height, 2 meters, okay, before the block touches the floor. So it's quite straightforward. We have 2 times the acceleration, multiply the height, 2 meters, and then square root to get the final velocity is 5.4 meter per second. So answer is B. So I see an interesting solution provided by these students. It used the energy of conservations. So I also would like to discuss about this because it's quite interesting to read. Okay, so what we can see again from the handwriting of these students is about mqh is equal to half mv squared. So clearly it's about energy of conservations. So we can see that when Q is falling, there is a conservation, there's a conversion of energy from the potential to the kinetic energy. So from here, I need to be specific about it. Okay, we can see the Q, the potential energy of the Q is reducing and kinetic energy is increasing. And we also cannot ignore about the P, that kinetic energy of P is also increasing since it starts from stationary to motion into a moving speed. So because P and Q are connected with a spring, so they are connected with the same speed. So from here, we can apply the energy of conservation. And here we assume that P is still on the surface. Okay, this is a very important assumption when we want to apply the energy of conservation, the conservation of energy. So we assume that P is still on the table. So potential energy of P is there as constant. So what we have is that the change in potential energy of Q, which is mgh. Okay, this is talking about Q, is equal to the change in the kinetic energy of P and Q, so half mv squared. So since they are moving with the same speed, so we would have the mp plus mq. Okay, so that is another way to do it, which is faster than the previous method. So the m here is referring to Q since we talk about the potential energy of Q. So here what we have is the mass of Q is 3 kg multiplied 9.81 multiply the height, okay, now it's 2 meter and equal to half 1 plus 3 squared. So when you try to calculate it, you will get the same answer as 5.4 meter per second. So you also can try to do the derivations that the both method can be linked, okay, they are connected, that we can actually find some similarity between these two cases, okay, the formula are quite similar. So you can try to derive it if you are interested. And for here, we just proceed to question 6. Okay, the ball move along a smooth curved track as shown in the diagram below. If the velocity of the ball at P and Q are VPBQ and the net forces acted on the ball, so the net forces should be the centripetal force. Okay, that's the definition of the centripetal force. It is the resultant force that causes the object to move in a circular motion. Okay, so the net forces acted on the ball at P and Q are RP and RQ respectively, which are the correct comparison between these two R and those two velocities. So by conservation of energy, we can see that there would be a conversion between the potential to the kinetic energy when you move from P to Q. So from here, we can expect that the velocity of Q is faster than velocity of P. The answer is either A or C. But here, I don't agree with answer C. So let's look at the formula of centripetal force. Okay, I mentioned that the net forces is the centripetal force. So it's given as mv squared over r. So it is still the same ball. So the mass is a constant variable. And we can see that the radius of these two semicircles is almost the same. So I think we can assume that the r is also a constant variable in this test. So the centripetal force would depend on the velocity. As I mentioned that the velocity of Q is faster than the velocity of P, we can conclude that the net force and the centripetal force at Q is larger than the centripetal force at P because the force is directly proportional to the velocity. So I guess the answer here should be A. Okay, we move on to question 7. The star of mass Gm Kx and the star of mass My are at the distance of L and 2L from the center of the earth, respectively, as shown in the diagram. So what is the ratio of the force that act on Earth by X and the force that act on Earth by Y? Okay, so between Earth and X, between Earth and Y. So the formula is F equal to Gmm over R squared. So just put in all the variables and do the comparison. So let's try to do it. So for the force between the Earth and X, so let us label as Fx. So it is equal to Gmm over R squared. So since it used capital M for X and Y, so let's label the mass of Earth as the small letter M. Okay, small letter M. Okay, so from here we can say that Fx is equal to Gm multiply the mass of X to M divided by the square of the distance separation. Okay, for here it will be L squared. So this is the force between the Earth and the X. Okay, now we're going to review the force between the Earth and the Y. Okay, label as Fy equals to Gm. Okay, multiply the mass of Y, M, divided by the square of the distance separation. Okay, 2L. Okay, so we need to put a bracket here, 2L squared. So simplify the equations, it is equal to Gmm over 4L squared. So for here, we can compare Fx and Fy, that Fx is at times of Fy. Okay, if you multiply it, you will get Gmm, 2 Gmm over L squared. So answer is D. Okay, add to 1. We move on to question 8. The mass and radius of Mars are this and this. Okay, what is the escape velocity of Mars? So we have learned how to derive the formula that escape velocity is the square root of 2 gm of r. So just apply the formula. So we have the square root of 2 gm of r. Okay, so the answer would be about 5,000 meters per second, and it is also 5.04 kilometers per second. We move on to question 9. The pressure of a fixed mass of an ideal gas from kinetic theory is given as P equal to 1 over 3 nmv over root mean square speed, where standard symbols are used. What quantities are represented by m and n? So I think these are what we have done before. The n here is the number of molecules, and the m here is the mass of a molecule. So molar mass is usually represented by mr, and Avogadro number is of course the Na. Okay, so the answer is A. We move to question 10. Okay, the graph of force against extension of a wire is shown below. The wire is stretched with increasing force just beyond the U point P. Then the force is slowly decreased to 0 at Q, as shown in the graph. So which statement is not true about the graph? First answer, permanent extension of the wire is all Q. Okay, correct. Okay, this is the permanent extension when the force is beyond the U point. Next one, the area of the shallow region represents the strength energy in the wire. Not so true, but yes, also. Okay, the area here is the energy recovered. Okay, when the force is removed. Next is C. The area of all PQ represents the energy that can be recovered when the force is reduced to 0. Okay, this is definitely wrong. Okay, the all PQ here is the energy loss. Okay, because the work done, the work applied on the wire is beyond the U point. Because a permanent extension means that there will be an energy loss that cannot be recovered, and that is the area of all PQ. So look at the last one, the area under the graph of OP represents the work done to stretch the wire just beyond the U point. Okay, that is correct. Okay, so the most wrong. Okay, the wrong answer should be C. While B, we could say it's not complete, but yeah, not false also. Okay, not wrong also. It's represent the strength energy. But it could be better if we can say that it's a strength energy recovered. Okay, we go to question 11. Okay, the speed of 6 molecules of a gas is U, 2U, 3U, 3U, 4U, and 6U respectively. What is the root mean square of the molecule? So I guess you should know how to do this. So by the word root mean square means that you get the square first, and then you get the mean, and you get the root. Okay, so this is the formula. So just go through the formula that we do the square first. Okay, square first means that you square all the speed. So the U, I think we can just put aside. We look at the number. So 1 square plus 2 square plus 3 square, and then 4 square, and then 6 square is 36. Okay, so this is the total of the square of speed. And then we get the mean square speed is, we get the mean is average divided by 6. So this is the mean square, and then we do the root of the mean square. Okay, so the answer is 3.54 U. So this is how you get the root mean square, and I hope you know how to do it. We move on to question 12. The molar heat capacity of an ideal gas at constant pressure is 7 over 2R. What is true about the type and the degree of freedom of the gas at room temperature? So here we can look back, the molar heat capacity at constant pressure is F over 2 over 2R, as we have derived before. So from the formula, we can compare with the expression given to find out the value of the degree of freedom. So here we can see that the F here should be equal to 5, which refers to the diatomic gas. Hence, the answer is B. We move on to question 13. A uniform rod PQ of weight W is supported by a cable as shown in the diagram below. R is the reaction force, P and T is the tension in the cable. Okay, which diagram show the correct forces that act on the rod? So the rod is not moving, so this is referred to the forces in equilibrium. So here the tension and the weight is fixed. Okay, the tension is along the rod, okay, and the weight is downward force. So here we just need to think what should be the reaction force. So here C and D is definitely wrong because we need an outward force to counter the tension and the weight. So it's either A and B. And if we look back the torque, okay, we can apply the torque to make sure the things is balanced. And then if you look at B, you can see that the reaction force is along the rod PQ, so this makes the answer B is wrong. Because when we analyze the resultant torque, let's say we put the pivot point at Q, we can find out that there's a resultant torque which is caused by the component W. We also can set the pivot point at the W here, and there is also a resultant torque. So the answer here will be A because you can see no matter where we set the pivot point, we can see there is a counter force which gives a different direction of torque to make sure the rigid body is in equilibrium. We move on to question 14, which is not true about the movement of fluid in natural convection. So quite obvious it is due to the mechanical means. Temperature gradient happen in the phenomenon of heat conduction, and B and D is not really related to heat transfer. We shall move to question 15. A material has high specific heat capacity and thermal conductivity. Under the same condition, which is true about the physical properties of the material? So first of all, specific heat capacity is learned in Form 4, okay, where Q is equal to mc theta. So here the answer is mentioned about the temperature and the flow of heat. So here maybe we can compare about the specific heat capacity C and the change in temperature. So as what we have learned before, the higher the specific capacity, the harder for us to raise the temperature. Okay, means the smaller the change in temperature. And as for the heat flow, okay, it depends on the thermal conductivity. So when the thermal conductivity K is high, means that dQ dt, rate of flow of heat, is also high. Okay, so answer is B. So that's all for the discussion, and thank you for watching.